Okay, today we're talking about Lewis diagrams. You may have learned how to do Lewis diagrams in grade 10 using a particular process. That process works for the ones you did Lewis diagrams for in grade 10. It does not work very well for most of the structures we're going to be doing diagrams for in grade 11 or grade 12. So what we're going to do is we're going to give you a much more complete picture. It's going to be a bit of a longer process, but it's going to be a process that works for pretty much any structure you're ever going to have to do a Lewis diagram for. So let's get started. There's going to be several steps. You won't have to do all the steps all the time, but you do have to at least think through them just to sort of check them off that yes I do, no I don't have to do that step. Your first step will be to count all the valence electrons. We'll talk about how in a couple of minutes. You are also going to have to add electrons for an anion. An anion, if you recall, is a negative charge, or subtract electrons for a cation. A cation is positively charged. Now right away we have to kind of remember the backwards thing in chemistry. So if I'm adding electrons, negative charge. If it's a plus charge, that means subtract electrons. So backwards I know, but that's the way it is. We're going to arrange our atoms, arranging the outer atoms around the central atom. So most of the structures that we're going to come into have one central atom, and atoms around that. How do we know which one's in the central? We'll get to that in a couple of minutes. Then we're going to connect those outer atoms to the central atom using bonds. And every bond, one bond, is 2 electrons. So we'll have pairs of electrons and bonds. Then we'll complete the octets. Now when I say octets, some atoms can't do the full 8. Think of hydrogen. It can only take 1 bond, which means 2 electrons. So I say octets, but it's not always a true 8 octet. Complete the octets of the outer atoms by adding electrons in pairs. Pairs again. And then we're going to add remaining electrons, if we have any, to the central atom. Again, in pairs. And then lastly, if. So we have to decide if it's necessary. But if it's necessary, how do I know? If the central atom does not have an octet. And I guess I should say minimum. We're going to find out that some atoms can go over the octet. And we're not going to run into that a lot, but often enough. Are there atoms that can't get an octet other than hydrogen? Yes, but very, very rarely will we have to do a Lewis diagram for those. So generally speaking, if we've got 8 or more, we're okay. Less than 8, we have to fix it. And that's where this last rule comes into play. So I'm going to tell you to pause it right here while you write this example down. We're going to work our way through these examples. Okay, we're going to work our way through the rules using these examples, so hopefully it all comes together. Don't forget that for this one, there's a positive charge there. So when you're doing that, there's a adding or subtracting electrons for the ions. Okay, so here we go. Job 1 is count all the valence electrons. How? Use your periodic table. So if you look at the periodic table, there's these group numbers above the columns. Now for us, we're not really going to do much with here. Mostly we're looking at the tall columns on the right. Okay, that's where we're going to be pulling our atoms from. And looking at some of those atoms, so let's say carbon. Carbon's in group 14. Ignoring that first one, 4 valence electrons. And looking at oxygen, group 16. Oops, that's not what I wanted to do. Group 16, not the 16, but the 6. That tells me how many valence electrons I have. So I use the periodic table to find the number of valence electrons. So going back to here, I've got sulfur in group 16, fluorine in group 17. So my valence electrons, 6 from sulfur, 7 from each fluorine, 4 of them, add them up for a total of 34. So my final structure has to have 34 electrons. Doing that for the others, I have 26 and 18 electrons respectively. Okay, second step was arrange the outer atoms around the central atom. Well, what makes a good central atom? If you've got multiple different kinds of atoms, and you always will, you're going to have to figure out what's the most likely central atom. There's a few things that kind of work together, a few things that you can use as clues to help you in that decision. Lowest electronegativity. So think back to electronegativity. What's the pattern? How do I use the periodic table for that? highest bonding capacity, which we probably don't know right now, but as we get used to these, we'll start to get a sense of that. But a bonding capacity is how many bonds can that thing take. So for example, hydrogen can only have one bond, not a good central atom. It's often the first atom written in the question, not always, but often. And often there will only be one of them, so that the central atom is unique to the others. Now what if you have one atom of 3 different types, and one's going to be in the central? Okay, so now we have to look at some of these other things. It will never be hydrogen in the central atom. If I look at the ones I had sulfur and fluorine or oxygen, so sulfur makes a pretty good central atom for each one of those. Next step, connect the outer atoms, fluorines or oxygen, to the central atom, sulfur, with 2 electron bonds. Now I don't mean 2 bonds, the 2 goes with the electron. So 2 electrons in 1 bond. So it's going to look like that. Well, that counts for 8 electrons. 2, 4, 6, 8 electrons. Doing that for the others, 6 electrons taken care of in bonds and 4 electrons taken care of in bonds. If I look at the total count, I've got a long way to go, but that's okay. We've got a few more steps to do. And the next step is complete the octets of those outer atoms. Don't worry about the sulfur in the middle. Complete the octets of the outer atoms by adding electrons in pairs. Really, really important to be in pairs. It's one of my pet peeves. It's also wrong if it's not in pairs. So it's not just a pet peeve, it's a wrong. Okay, so for this one, I complete the octets of the fluorine. So 2 electrons in the bond, 2 in a pair, 2 in a pair, 2 in a pair. This now has 8 electrons, and I do that for each one. That now counts for 32 electrons out of my total count. Doing that for the other ones. 24 for my total count, and this one 16 from the total count. Now in each one I've got electrons still to put on there, so next step. Add the remaining electrons in pairs again to the central atom. So for the first one I put 1 pair there on the central atom. Now what I mean by in pairs is I don't want to see, so bond, 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 electron, electron. That's not a pair. Yeah, you put 2 electrons down, but they're not paired up. Well, it's more symmetrical. Doesn't matter. In pairs. Now I've got 34 electrons. So compare that with your original final count. This one, I have 26 electrons. And this one, 18 electrons. So in each case, I have my full count of electrons taken care of because I put the remaining electrons on the central. Could it be that I would have more than that? In each one, I put 1 pair of electrons. Yes. Sometimes you'll have more pairs of electrons than just 1 pair. Okay, we had one last rule, and that was if. If the central atom does not have at least an octet, then make multiple bonds. So having a look at this one, the central atom has more than 8, I don't need to use this rule. Looking at the next one, the central atom has 8, so it has its octet, I don't need to do anything else to it. The last one, the central atom did not have an octet. The central atom only had 6 electrons around. So how do I take care of that? So I've got 2, 4, 6 electrons on my original, I got all the electrons down. I move one of the electron pairs into a bonding pair. So right here, where it was non-bonding position, oxygen had both electrons. Now I'm going to make oxygen share those electrons. Well, which one do I do? Doesn't matter. Now, some cases, if let's say this side were fluorine and this side were still the oxygen, which atom, oxygen or fluorine, is more likely to make a double bond? Well, then it will make a bit of a difference. We'll kind of pick up some of those subtleties as we go through. For right now, it's not going to happen all that often where one side matters more than the other side. Once in a while. But I think you can use some common sense, some chemical sense, to figure that out. Alright, so I'm going to leave you with a few to try. We've got some ions going on. We've got some non-ions going on. What I want you to do is try these, go through all the steps. I'll check them tomorrow, one way or the other. Either I'll walk around and I'll check your stuff, or I'll get you put in the half book or something like that, and see what we've got with that. And then we're ready to try a few more in class. Okay, talk to you then. See ya.